welcome to this hybrid event arranged by the IET Angling Coastal Local Network, which represents members in North Essex, Norfolk and Suffolk. Welcome to those of you in the local audience here at the atrium at the University of Suffolk. Welcome also to folks joining via Teams from other parts of the UK and indeed globally. I'm Kevin Foster and I chair the Angling Coastal Local Network, and I'll be your host for this evening. So without further ado, I'm delighted to introduce our speaker, David Atkins. David is an entrepreneur based in Ipswich, actively building three businesses, 3A Design, ICOTest and Frame, while also contributing to community initiatives such as Film Suffolk, Innovate Suffolk and Ipswich Makerspace. David has a broad background in electronics design, including FPGA, analog and RF, as well as software development across a range of applications, from low-level microcontrollers to large-scale broadcast content management systems. David is passionate about nurturing the next generation of talent. He works closely with the University of Suffolk, mentoring 2 degree apprentices and 2 interns. So David, over to you.
Thank you. Move on. So, yeah, I've been in Ipswich for more years than we care to think about nowadays. So never quite escaped. At various times in my life, been involved in what's now, well, Screen Subtitling Systems is now Screen Systems over in Claydon. Back in '91, while I was at university, I got involved in the start of that. And then Suitcase TV from 2000 until 2019. So 3A Design and was my 2019 start, and then ICOTest and Frame and followed that. Only I'm doing them all at the same time now because I'm very foolish and try to do too many things at the same time. So what we're here to talk about today is live production and why we might want to not do it the way that it's currently done in broadcast. If you've ever seen a football match, you'll probably spot at least a couple of 40-foot trucks out the back of the ground that will have expanding sides, and they'll be rammed with people having a very awkward time inside these things. They're very expensive trucks, and even if the truck's equipment is back at base, it's the same equipment. It's very heavy, expensive equipment that is being installed in racks. So these are just some examples of these kind of OB trucks, and you can kind of see 72 vision inputs going into the mixing desk on it. That's going to be a million straight away just for the mixing desk that's performing the video side of it. Loads of screens, recorders, replay systems. They come in at about $250,000 a pop. There's probably half a dozen at least of those on board to make it work. Talkback, and you see once the thing's expanded, it's 5 meters across, so the whole side of it pops out to try and make space for people in it. And then if you look at the inside of it, so it's not quite the same truck, I don't think, but as an example of these, you're probably looking at between 5 million for this, up to 20 million plus for a big truck. Increasingly, we've got 5 of them now, which is great, because 5 is much lighter than copper. But originally, these were all built with coaxial cables at 75 ohms. So, very, very old school cabling in them because it works and people understood it. But yeah, there's panels that pop out everywhere to get all the connectors in and so on. And then to power it, there'll be another truck with a generator in it as well. So you've got to have a generator truck just to make it all work. It's awesome how much stuff there is. And if you do something like the Olympics, you might be running 100 events in parallel. So you might have to have 100 of these things knocking around to make it work. Generally horrific. And inside, while it expanded to 5 meters, what they've done is given 3 working desks in the 5 meters distance. So you're all rammed in there with kits in a fairly cramped environment. This is not a good accessible environment for people. It's quite exclusionary on who can actually get into the thing. You look at the steps you have to go up and creak the way up the steps to get to the damn thing. It's all very difficult and probably unnecessary. I think that's actually 4 desk positions. 1, 2, 3. I think it's got 4 desk positions. But yeah, I've been in them. They're not pleasant in working environment really. I've seen the F1 doing it. They take huge tents with them, and they make the walls of the tents out of the sides of the containers that all the kit is in. But then they have 200 people in there, so you don't do much better, and it's really quite frenetic. So and there's obviously some issues here. You can only use the kit when it's parked and powered up. So, you know, if it takes a day to get there and get things set up, you run the thing for 3 hours to do the event, and it's a day to get it back again. The efficiency on the equipment is really low, and the capex you spent is horrendous. All the staff have to go there. So, you know, if it's in Paris, we might be shipping 100 people across. I went to the 2016 Euros in Paris with BBC. We were doing some trials with them then, and they had 130 people on site for the Euros. And every 10 people had a manager. So the first 100 people had 10 managers with them. I said, which meant that 10 managers had a manager as well. So we're up to 111 already. So you can see the complexity. That's just horrific in terms of moving people around. Euros last for weeks, so they've got to rotate people through because they've got to have leave. Hotel rooms, food, everything is a very expensive way and very not green, I would argue, by the time you ship the stuff around. I mentioned the poor access to the environments. And they are designed to do a job, and very much they'll be designed to do one kind of role. So a sports truck will do sports. Be very hard to reconfigure something else because you probably don't need all the replay gear in it. So this is quite a painful way of doing things. So I say there is an increasingly people are leaving the kit back at base and taking a truck with all the cameras and stuff in it. But to test that, you still have to have kit on site to allow you to see if it's working. So it doesn't quite win the argument for you. And I mentioned the 130 people, the number of people involved in these kind of productions. This is a more general thing of actually doing episodic production as well, but the number of roles there are in it. And these roles are very narrowly defined. You know, the sound guy will only do the sound guy. You know, he won't touch the lighting cable or plug something in for someone else. If you go to the States, this gets worse. It's really amazing how narrowly defined things are. And then the poor old runner who's running around trying to get cups of tea for everybody and keep everybody happy with coffee. But that's very much the entry level. You come in as a runner and you try to prove you can do something else to get up the rankings. So, but a Premier League match, 24 cameras moving on the pitch. So that's 24 camera operators on the pitch. And all those cameras will be 4K cameras nowadays. Each camera produces 12 gigabits of data a second. So that's 300-400 gigabits of data coming off the cameras on the pitch. And then you've got the ones on the talent around the pitch and the ones doing crowd scenes. There's a lot of stuff going on in these things. So it's not a simple operation. And the signals, so good old days, I'll reminisce about analog TV, fortunately pretty much gone now. So it was on 75 ohm coax. The digital TV went to 75 ohm coax because we had all this 75 ohm coax in the facility. So we must use that for our new setup. So we managed to stay on 75 ohm coax all the way up to 12 gigabits. I mean, if you look at the way that stuff works, you kind of go, really? It actually works. There's no forward error correction. It's just a bit waggling up and down. It's quite astonishing it works at all. But it's heavy coaxial cable. Nowadays, SMPTE 2110 is effectively RTP over UDP, if you boil it down to its simplest level. But up to 12 gigabits of RTP, traveling with no protection, no nothing down the fibers, quite often over multicast as well. So it's quite an exciting set of data going through your switch. And our equipment's updated over it. Once we get to the cloud, this gets different. You can't unplug a cable and plug it into your oscilloscope and have a look at it anymore. That's gone away. So we need to think about how do we monitor these live systems. And in the cloud, we may not be in the same building, let alone it could be distributed across a much wider area. Gets interesting at that level. So we've been working towards how can we get rid of all the specialist kit and just use software. So we want to get signal off the camera as simply as possible. There are protocols that will do that. So typically, if it's being sent over the internet to get to a broadcast facility, you'll take the 12 gigabits. You might compress it down to a couple of gigabits of JPEG XS to avoid losing any quality. So now we're only bringing back 24 to 52 gigabit signals over the internet. Every Premier League ground has fully redundant 100 gig networking in it for this purpose. So they've planned ahead. It also means that BT have to guess which teams are going up next season to make sure they manage to get the fibres in to the ground before the season starts. And you can imagine the number of wayleaves and things you need to get fibre installed at some of these sites. So at the other end, we want to be able to use any device that you might have to hand to access the system. So if a phone's the right device because you're mobile, you should be able to use your phone, or it might be a laptop, it might be a desktop. We don't want to care at that level. So we've moved to using web browsers for everything. So there's no specialist software, no installable apps. It's just HTML, and that's all we use. When we come to the compute bit, we want this to be as simple as we don't want to have to think about who's your provider of your compute. So I don't care if you're using AWS or Azure, our system just has to run a bit. Broadcasters are quite conservative and like to protect their interests. And if you're running a system 24 hours a day all year round, running on AWS can be very expensive. If you're running for 2 hours on a Saturday, AWS is probably the right thing. So there will be breakpoints where it's better to have your own compute. So somebody like Warner Brothers Discovery, who they took over BT Sport, they run all the Olympics footage and Lord knows what else around Europe, have built 2 massive data centers that have 250,000 10 gigabit Ethernet ports in them. You don't want to think about updating software and that kind of thing at that scale if you don't have help. So the on-prem model is still very dominant because it can reduce costs. And then if you want to run your spikes of transmission out to AWS, then maybe that's what you want to do. So we've had to work with we cannot have an opinion about your provider. SIMPTE is the Society of Motion Pictures and Television Engineers. I'm a member again. I finally signed up properly. So they have an annual conference in Los Angeles, the Media Technology Summit. I think it's what MTS stands for. We did a joint demo with a company called Appear. So we provided all the equipment. They sent somebody to California to go and talk about it. So we had feeds from Felixstowe, a feed coming out of a shopping mall somewhere in Los Angeles. I'm not quite sure where. I wasn't there to tell. And then we have a couple of cameras in our office that switch on exciting things like lava lamps and little Chinese waving cats. They're always moving, being fed into the system over various protocols. So from Los Angeles, it was actually coming from a mobile phone, I think. So it was Larry's broadcaster running on a phone, turned your phone into a pro video camera, uses a protocol called SRT, Secure and Reliable Transport, which basically hardens the UDP connection up so you won't lose data. I think Felixstowe, we were doing the same thing to get the system in. So it hit our system. We then decode everything back to actual video, uncompressed video, feed it through various bits of processing, create multi-view so we can send it to an operator so you can actually see what we do in the video, because you can't see it in the cloud. That's not where people are. The operator makes various editing choices about what's going on, and then the feed was going out to YouTube so they could watch that in the venue. I have a demo later, so I'll come to that, which have moved on somewhat from that. So just to get into a bit more detail about this, we're using containers, and now we're using pods and Kubernetes nowadays. So we're moving into a Kubernetes environment. The scale of some of these systems means we will have to run hundreds or thousands of containers to make one production happen. So you can't have people thinking about this too much. We have to automate all of that stuff. So Kubernetes is part of the tool set. It doesn't do everything we want. We've had to add lots of functionality into the operators and stuff within Kubernetes to make that work for us. But down at the simplest, we bring in this compressed video stream, or possibly uncompressed. We'll decode it back to baseband. We produce a scaled copy of it, because if you've got 50 cameras and you're looking on your mobile phone, you don't need 50 4K signals being sent to your phone. It doesn't work very well. So we produce a proxy resolution at 640 by 360 resolution, which we use for all the operator feeds, because you can't get much more than that on the screen. All of those get fed into this VDI layer, which I'll talk about in a minute, and then this just scales up. So if I need 10 nodes to run all my input processing on, I have 10 nodes to run it on. And when you start to look at the architecture of systems, you can be quite clever about the way we move data around to make it efficient, because what we don't want to do is move any of this stuff over the network if we don't have to, right? Moving it on the processor is much more efficient than going to the network. So that was the input side. So when we're mixing videos together, we have a relatively simple module that will take these 2 feeds in real time and multiply them by the alpha signal. So we have how much of A do you want, and then we have the inverse amount of B. So we only ever end up with one at the output. And then we can crossfade between the two feeds. So we can switch between the A and the B input on here. And then typically what we'll have is a graphics feed coming in, which has actually got logos and graphics on it. We'll see what those are later. And again, there'll be a master fade on this. In practice, in a big system, this might be 8 layers deep. So we might have multiple layers. We'll have picture in picture. We'll have lots of graphics coming from different things. So we'll be like, we've seen football on TV. They've got logos and scores and replays. Horrendous amount of stuff going on. So an operator, they need to see all of this synchronized. So we've got to get the signal to them and guarantee that all the videos relate to the same point in time. So if we've used Teams, we kind of know that sometimes it gets a bit laggy. And the protocols we've got for doing this are fundamentally really WebRTC. It's the front runner in getting video to a browser. So what we do is we don't send all the videos to the client at all. We cheat. We assemble the whole thing in the cloud into one video. And then we compress that and send the one video to the client. And that means we can also guarantee the audio synchronized. So we can do things like take the program audio or the audio you want to listen to, plus talkback. Talkback is how the people producing the program talk to each other. So the director will be yelling at camera one to go and get a better shot of Beckham or whatever it is that he wants. I can only think of one football player, and that's Beckham, so I'm stuck there. Not a football man. And what we do with these is we run these through scalers that position the video in the output window. And when we look at, you'll see that typically that could be 12, 20, 30, 40 videos being put into one feed. But each of these things is a very simple bit of software in principle. The only problem is it has to be able to process an awful lot of data every second very reliably on the tick to make this work. So that we write that in using AVX2 instruction set stuff, which is the hardcore, very long word, very long data instructions in the CPU. So that's my part of the job when it comes to writing software. So we're now working on replays. So when we see slow motion replays and stuff on TV, most people think of that as an EVS product because they seem to own that market. But at 250 grand a box, they're doing really nicely, and it's recorded on disk. So we want to move away to that to something that looks like S3 storage. So the BBC have published a new protocol called TAM, or Time Addressable Media. It's an API that allows you to go, I've got a second of video, I've got another second of video, I've got another second of video, and assign S3 URLs to it. So each second is in a separate bucket, in a separate object on S3, all wedged together in a bucket. A bucket is a collection of storage on S3. And then we can go back and request from it the range of clips we want to play, reassemble it, and play it back. Now, we're doing that uncompressed. We're using S3 storage uncompressed, so 12 gigabits a second being written to S3, possibly times 24. So Amazon will like this a lot because we'll need storage. But actually, S3 is designed to work like this, and there's a product called MinIO, an open source version of S3 you can run on your on-prem. And if you like paying for it, you can. If you don't, you don't. So, and that provides exactly the same API as S3 does. So that's what we're using when we're not on Amazon. So yeah, the playback side of it is just assembling these clips. You quite often find in these trucks there are people sitting there marking the shot. So there'll be one guy who's got 4 cameras and he's watching all 4 cameras, waiting for something interesting to happen. And then he'll go mark where the beginning of the interesting is, where the end of the interesting, put some text in it. And then the director will go, has anyone got that goal? And they'll try and find the best shots and then they'll play them back. But they're doing this like for 90 minutes solid. They come out looking completely dazed by the thing that they're doing. So we've got all this data flying around. When we're working on a single instance or a single node, then what we try to use is shared memory. Shared memory is running at the full bandwidth of the main memory of the machine, and we use that to pass the data between our containers. And you can get very secure transfer because you can set up a complete user domain for it, and that just means no one can access your data unless they've been signed into your domain on that node. We can run multiple tenants on the same machine. They cannot see each other's content, which is great. Eventually, though, we can't get any more stuff on one box. And now we have a problem because we have to get it to another box. So we could just use the operating system networking. But if you use operating system networking, it doesn't work because the data rates are so insanely high. So we cannot do that at that level. So we use a technology called RDMA, which is the network card has its own operating system and runs the transfers for us. So it's running its own IP stack. And what it can do is reach out into the memory of your system and pull the data directly from memory, using the scatter gather and virtual pages, all the stuff it has to do to get that out in the right order, assemble it, throw it into the network switch. At the other end, the other network card already knows that you're going to send it to it. It knows where it's going to drop the data off when it arrives, and it'll write it out into the memory. And then lots of clever software sits and goes, something's happened and we can process it. So this RDMA technology isn't used by many applications. A few use it where you need lots of high speed. It's used in AI particularly because you can go from the network directly into the GPU without the CPU knowing about it. The big plus is the CPU only gets to say, set up these transfers and then do nothing. So CPU utilization is incredibly low on these things, which is what we need. So we want the CPU to do all the video processing. So we're using that. And these cards are what was Mellanox, now is NVIDIA. They supply 90% of data center cards. So we know pretty much every chance that you have got the right cards in your network. And the switches in the middle are just fairly conventional big iron switches, but a one-use switch can have an insane amount of traffic going through it. I think I had some numbers coming up on this. Oh, right, so that was a low-level RDMA. We use a library called libfabric, again, open source. libfabric has providers written by the network card network card manufacturers that basically package their protocol in. So we use libfabric to package up our data. VDI is our virtual digital interconnect. It's our internal bus for how we move stuff around. So as long as it's in one of our VDI memory pools, we can get it to any instance on any node in our cluster that we're computing on. If you're on AWS, you have to do this within availability zones because once you go outside, the latency is too long. But within the availability zone, they don't charge you for moving 500 gigabits of data a second around. It's kind of convenient. So they do charge you, obviously, by charging you for the instance and the amount of networking you had to have on it. But the actual data is not a chargeable event. We've been doing quite a lot of testing with this, and we want to be able to do this on everything from lightweight systems that don't cost the earth to massive systems, and we'll get to what that means in a second. So these very simple ConnectX 6 cards, I think they are. I think I may have paid 70 quid for each one on eBay for the test system. The QNAP switch we're using in the middle is 25 gigabit. It's $1,000 off Amazon. So this really is common off-the-shelf hardware. There's no two ways about it. We have done nothing clever to get to that point. So our setup is using both transmit from one to the other, receive back, and also bidirectional flows where we're sending at the same time in both directions. And we've been using both 8-bit and 16-bit video. I'll come to why that's important in a second. The color format that we typically use in broadcasting is YUV. So it's Y is the black and white part of the signal. U and V are the color difference signals that you're left with once you've taken the black and white out of the image. And 422 means we're using effectively temporal compression. So the color signals are at half the resolution of the black and white signal, right? And that's just how it's been done forever. And the A on the end means we're carrying an alpha channel, so we can have a mask that goes with the data. So the important thing with this data I'm about to show you is it's single threaded. So there's only one core working on this job while we're running it. And we're still only using standard size frames. We could have gone to 9K frames, but that'd be cheating. So, what we have here is the various frame sizes. So I think at the top there, we've got the smallest one is sort of 1080p at 4 megabytes per frame, up to the 16-bit 1080p with alpha, which is 12 megabytes a frame. And in the UK, we'd run that at 50 frames a second. So that would be 600 megabytes a second for that bottom one, or lots as it is for the bits on that. So at the smallest end of that, the latency of the network is under 4 milliseconds from one node to the next. So we're moving those 4 megabytes in 4 milliseconds from one end to the other. And the CPU usage for 4 megabytes per frames is a massive 5.5% of one core of a 16-core system. right? The only reason that's so high is that at 4 megabytes a second, we've saturated the 25 gig network. So we're actually sending 600 frames a second. So we've got 600 transfers we have to set up per second. So when we get to the other end at 12 megabytes at a time, we can only do a third of the number of frames a second because of the limit on the bandwidth. So now the CPU comes down because we're using a third of the CPU to do the setups. But I mean, you barely know the system's being used at all. And we're completely saturating a 25 gig network at that point. And now we can buy 100 gig networking and 200 gig network and 400 gig network and very soon 800 gig network cards. So we can go a long way with this. Is there anything else I'm going to do on that? Yeah, so the packets per second, that means that at that lowest resolution, we can be sending nearly 600 frames a second over that 25 gig link at that 4 millisecond latency. So you can't do that on the old standards because they take a frame to get everything to the next point. So, I've said most of this already, but just to call it out, I can now buy a 128? Yes, 128 port, 400 gig switch. So that's 400 gigabits on every one of those 128 ports for just under $50,000. It'll cost me $60,000 for the SFPs to make it work, to get the fibers into it, but let's not worry about that tiny little detail. But that means I can have 10,240 bidirectional flows going through that 2U switch. And that one's air cooled. It's just, these things are amazing. So I have seen quite a lot of water cooled switches, which effectively have hose lock connectors on the front to try and stop them melting. Multi-viewer, this is what we'll have a look at on the live demo shortly. So this is what's being rendered by all that compositing to make the feed. So these will have rolling videos in it. This is controlling the graphics. So the Synty logo is being injected by us on the feed that goes out. And we can select the camera feed angle we want from there. All of these displays are designed in a web application that lets you design the web application that you're using to control your system, because every broadcaster is different and every operator wants a different setup. So every operator can have a different configuration with different feeds coming to them to suit their actual role in the operation. And we have made sure that nothing we have is anything but a web application. And when I say web application, I mean an HTML page. So that's been quite a challenge to build it, but we're doing quite well at that now. And we had to do things like audio. So an audio mixer has thousands of knobs on it. Very hard to get that on a screen, but what we do is we have small banks of these controls, and then you can rotate through pages of your audio mixer and look at one channel at a time. I saw today in the demos at lunchtime that we've now got the control of this being tied to physical panels as well. So you can have a physical panel and it's tied to the virtual panel that's on your screen. And then that's shared across all the operators. So all the operators see the same thing happening exactly the same time across it, because they have to. So they're all working together. They need to have a fully synchronized view of the world. So that's actually a screenshot of the designer. So we're trying to create that physical interface over there on screen thing. So we know how to get there. So the live demo looks quite a lot like that. I think I've got, yeah, it is that. Excellent. So my live demo is this picture here. Excellent. And I took the right thing. So we've only got 3 cameras on it. It's also using a protocol for the connectivity between software modules, which is called the VSF's GCCG protocol, the unlikely named ground to cloud to cloud to ground protocol. So this is an uncompressed API for transmitting the 12 gigabit streams around the network. We got involved in this towards the tail end of last year. We got involved in it because we had a working system that actually did this. They didn't have anything that worked. They had a protocol. So we've gone through and helped them get to the point where they have a working protocol by taking our learning and building it into it. So this was the first demo of this actually in public out in Los Angeles a couple of weeks ago, where we had a system in Oslo, which is where the cloud is. We had cameras in Los Angeles and Ipswich feeding into that cloud in Oslo. And then we were sending the feed back to a screen in Los Angeles so we could actually watch it and control it. So we'll get most of that here apart from the output stream, because I've run out of network connectivity and stuff in here. So that's what we are going to see shortly. Right, we got to the end. It's the demo. Right. The wise amongst you will probably notice that it's not that sunny outside right now. It's the peril of doing these things at night. So these are 2-minute loops that I've shot with a camera from various parts around the docks at various times of the year. I think these were a couple of weekends ago. I really want to get the big wheel in before it goes away, but I failed to get there at night when the lights are on and it's moving with a camera that I can do the recording with, so I'm going to have to get that done on Saturday, as we can see. So up here we got that camera we're selecting at the moment. This is actually a satellite decoder in Oslo, which is outputting a compressed video feed on IP over transport stream on UDP. That's been sent into one of our partners' boxes that turns it back into SRT. And then we're taking the SRT into the system, decoding it, turning it into baseband to get it into the system. So it's slightly complicated, but we were trying to make the point of the demo that you can do almost anything with the setup that we built around GCCG. And then this is another loop playing out. So we're streaming the loops out of our office in Ipswich over in Silent Street. They're going out on the internet over SRT, are being pulled into the box in Oslo and decoded. These two control panels control the graphics players. So we're using a product from a company called Singular Live, who have web-based graphics generation. So we're using their really cheap tool, which is free, as opposed to their $20 an hour one, because then I'd forget to turn it off, which allows me to bring the graphics up. So we can see the appearance frame up there. And from here, I can choose to have it be all frame if I want, by selecting that. That's communicated with the AWS instance running Singular, which runs their Uno product. And then we have a renderer that is effectively an HTML renderer running in the cloud in Oslo, which is generating the foreground image and the key that cuts the hole in the video for the logo to shine through. And then that's fed into our overlay engines to create that effect. It feels very complicated, but actually this means you can do anything you like with HTML. And HTML is really becoming very powerful at doing these kind of graphics because it just works. And everybody has a web browser. And you take the URL, you can watch it in your web browser without having to have anything special to see how it's working. So, and then finally, let's do some swapping around on feeds. So that cut has involved a signal being sent from my browser. We use MQTT as the messaging protocol for real-time control, which goes over WebSockets in HTTPS back to a broker running in the cloud, which then sends a message out to all the people listening to it. And there's a thing that runs the video switcher that's selecting a video, sees that, cuts the high-res feed. So it's now switching between the various 1080p pictures, writing it back into memory because we use VDI to go back from the switcher back into memory. And then a compressor's picking that up. Sorry, not compressor, the compositor picks it up, sticks it into this view here, writes it back into memory again to create the VDI version of that feed. And then a compressor picks it up, compresses it into H.264 at a couple of megabits in 1080p, sends it through a WebRTC engine, which sends it to my browser, which then decodes it. So when I hit this button, that's when the action starts. And what I like about this is that the latency between me doing that and it changing on screen is about 120 milliseconds. We can go faster on the right network. So I'm running on the university Wi-Fi and the guest Wi-Fi here, so I have nothing special going on at all. So the green counter at the top is the number of packets we've lost on the WebRTC feed. WebRTC is SRTP, so it's RTP with encryption. So if you lose a packet, there's no way of recovering it. But that's why it's fast, is you don't wait and try and recover it. It just hammers it through as fast as we can. And we need that to keep that latency down so that when you're working on it, you're working as close to real time as you possibly can. The odd looking clock at the top is one of the timing things we use. So we add this in everywhere. And the dot is just to make it really easy when we take a picture to work out which frame we're on. Because sometimes if you take a picture with a camera, it will be on 2 frames at the same time. So you kind of get a blurry splodge. So, and that's actually just a web page as well. So that's just an iframe in the HTML page that is this thing dropped in. So, and just in case anyone's going, that doesn't look like a web page, let me just take it out full screen. I'm just in Chrome, right? So it really is a web page. There's no trickery going on at this point. But most broadcasters basically want to use the whole screen for the thing that they're doing. So we allow that to happen. So I will show you a couple of other things. I talked about design side of this. So let me see if I can get to the designer. So we're looking at that screen there. If I jump into here, let it load. What I can do is go and find that layout, and we're on, I think, that one there. So if I load that, so I've loaded the configuration we're looking at, and now I'm in here, I can go and adjust that configuration, move the windows around, add Windows components to it. And again, it's just in a web browser. And I know when we tried to do this 10 years ago, doing this in the web was just not a thing. Browsers couldn't do it, HTML couldn't do it. Things have moved on so far, it's amazing what we can actually get to work with now. So from here, we can set up the streams, what they're associated with, the camera feeds are coming from. I'm trying to work out if I'm about to be ridiculously brave. I'll show you the editor that I have in here. So this is a live system at a customer site. So I suspect what I'm going to find is that I've got a slightly older version of the system designer here. The system designer is there to help you draw the system you want to operate. So drop a camera in, drop the mixers in, and connect the whole thing up. And it looks like the one that's in the system at the moment is not quite up to date. The tool we use for producing these applications, so all these applications are actually written in Python, even the HTML pages are in Python, and then we transpile that to JavaScript and a tool called Anvil that does all that work for us. So we don't have to have a host of languages going on, we can just use Python for everything. I'm not even going to try and guess at what the URL to that one is because I'll probably get it wrong. So I think that's all the slides that I had. So is that where I was? So, yes.
Thanks very much, David. Thanks for an excellent talk. Thank you very much. I will move into some Q&A now.
Yes.
George, I think you're on the online one.
Yeah. I don't have any questions yet.
Okay. So if you're online and you think of a question, please put it into the Q&A panel. Whilst we're waiting, we'll take any questions from the audience here in the atrium. Does anyone have a question? Mark.
Do you use a JavaScript toolkit, or does Anvil do what? I haven't come across that one.
You hit run and it does it all for you.
Does it?
We use some JavaScript modules, but we import them into Anvil and it wraps them in Python for us, so we don't have to know how they work.
Right.
So, but obviously what's running the web page is JavaScript.
Yeah.
And the transpiler just makes that up at runtime from the Python code. But it has allowed us to build a lot of things very quickly without having to get tied up in, are we using a React or some other library?
Yeah.
Somebody else does that bit, we don't think about it. And we found no performance issues from doing it. It just works. What I really like about it is we've also been able to take the container backend that runs the Anvil backend, and we run that on a Raspberry Pi on some of our other products. So we can actually put it on really low-end products on a microcontroller and have it hosted on there, still have a fairly fully functional web page very easily out of it. It makes it look like you've done a lot of work, which is what I like about it. So,
Felix, I've got a question.
Thank you for your presentation. And my question is on the latency aspect of it, because you mentioned about satellites, having the cloud in Oslo, then you are transmitting from Ipswich here. And once satellite is involved, definitely there is, latency. Earth to satellite, then satellite, back again. So
satellites,
your 120 milliseconds. So I don't know how you achieved that wonderful,
So satellites are now very last year in broadcast. They're expensive to get up there. It's quite crowded up there, and broadcast satellites are in geosynchronous orbits, so they're a really long way away. So you get about a third of a second just with getting to and from the satellite, and they're criminally expensive to use. Fibre on the ground, it's cheap now, very cheap. You can get a very fat connection for virtually no money, almost anywhere in the industrialized world. And products like Starlink, if you're running a camera out of Ukraine or South Africa, a 10 megabit uplink would be amazing, and Starlink will handle that. And because it's a low Earth orbit, the latency is tiny.
Yeah, I know.
Yeah,
20 milliseconds.
Yeah, so actually, it's not the issue it used to be. Satellite might still be involved in the distribution of the signal to the customer, but that's only one hop, and then 300 milliseconds. Who gives a damn? The MPEG-2 or the H.264 compression is 2 seconds at that point. That latency is lost in the noise of all the other stuff that's going on. For us, latency is critical around the user interface, so that if I have 5 people in different continents and they all hit go at the same time, they should all mean now. And what that should mean is exactly the same time for everyone. So we have to make sure we synchronize everything. When you press a key, we capture the time you press the key, and we send that back to the central system so that it will apply the action that you've selected to the frame that you were seeing. So often in the back end, the high-res content is traveling behind the low-res content. So we might have a 3-frame delay to allow the signal to get out to the operator and back again, so we can make those cuts look right. Because what you really want to happen, if you're cutting to the ball being kicked, you want to see the ball being kicked, not the ball has been kicked. It's a bit unfortunate if you get that way around. So it's very important we can maintain that sync. Which getting time accurate to that level can be very complicated, but in reality, we have to be accurate to the frame. So we're using time that's accurate to a nanosecond, but we kind of go, if it's plus or minus 5 milliseconds, we're fine. We will have the right shot, right? So, and we're also moving to use TIE, so atomic time, not UTC. The problem with UTC is it has leap seconds in it, and we can't have anything but monotonic time. So we're only 37 seconds away from UTC at the moment in TIE time. So, and then of course when we get to operators, quite often they want a wall clock in their local time, but it has to be synchronized back to master time. And at that point, satellites are great GPS because they just do it for us. We don't think so much. So.
Thank you very much.
George, have we a question?
I don't have any from the webinar yet, but I'm going to encourage them. I'm going to ask you a question myself. I remember a pal of mine who was in the BBC at the time, some years ago, talking about the potential for ISDN and things like that to support outside broadcast in wholly innovative ways.
Yeah.
Have you had any discussions yet about the way in which this kind of technology could revolutionize some of the content production and new kinds of programming enabled by the technology you've got?
The things that make that interesting is possibly not ISDN. I think we'll pass that one by now.
I wasn't saying ISDN.
We'd have to tell people what it was to be able to talk about it. But 5G is really starting to become quite solid and reliable for data transport. Rubbish for phone calls as far as I can tell. But if you want IP, it's really quite good. So a lot of content recently, so things like the funeral, the Queen and the coronation, a lot of that was acquired and transmitted over 5G. Quite often by having those kits will have 4 different network providers radios in them. So they'll have 4 phones with different SIMs in it, and then possibly another one of each just in case. And the data will be spread across it and bonded together to make a higher bandwidth connection that's resilient to the fact that the cameraman keeps wandering around and turning. We all know what happens when you move with your phone onto this stuff. So 5G is really powerful in that. I think Starlink will be, and similar technology will be equally powerful. Wi-Fi is difficult. Wi-Fi is very poor at multicast, for example. If you send one packet, any multicast traffic is sent at 6 megabits a second.
Yep.
So it just ruins the network for you because the whole network has to run at 6 megabits while you're doing it. So if you send a 6 megabit multicast feed, the entire Wi-Fi is out. Everyone is suffering your rate. So ideally, you don't want multicast on Wi-Fi as a result. So we're using unicast here because we can put probably 10 6 megabit feeds through your unicast and one on multicast. So Wi-Fi is difficult to make work, and it reassociates so quickly and so slowly as well as you move around. So 5G, I think, has just a much better performance at switching between base stations. So that makes a difference, and the fact that fibre is so prevalent as well.
Even though that normally needs Wi-Fi at the end of it.
Yeah, there is that detail. I was looking in here for a wired connection earlier on and eventually gave up because
I'm sure there are some.
yeah, but they're quite secure. I may have tried, but or I didn't. This case may be.
George.
I've got another one from David Blake on the webinar. And David says, you spoke of the large amount of equipment and resources and vans needed to record an event. Are there any new approaches to help reduce the volume of vehicles, or are people already looking at the ways in which they could actually make some savings there?
What happened during COVID is people went, we don't have to take all the kit there, we'll just send the camera, the trucks and the people in it. But you're still sending camera, and cameras are expensive. The lens on a camera for sport is about £75,000. And okay, that survives generations. It's just a bit of glass. It doesn't have any resolution itself. But you know, an HD lens and a 4K lens are not the same thing because they have to be better quality glass. So that's an expensive thing. But when you move the cameras there, you need somewhere testing the cameras when they get there. So you need some other kit to do that, and you have to terminate them. So you can reduce it, but then the kit you had in the truck, you now have to have in a rack where your base is. So a company called IMG based down at Stockwell Park. If you do football, you might have heard that being mentioned in the replays, because that's where all that happens as well. And they just have racks and racks of the kit that used to be in the trucks in racks on their premises. And they can still only use it for the match when it's there. Whereas by using a computer to do this, when we stop doing the match, we tear down the whole system, just shut all the containers down. Bingo, we're not paying any more for it. So we don't pay for it if it's not in use. And by using Kubernetes, we can make that very quick and efficient. So we can go, right, close it. So one of the reasons we want to use Kubernetes and a DevOps approach is we want you to design your system, commit it into Git. So we're actually integrating GitLab as part of our Kubernetes framework. So you will commit to Git your change, you'll merge it, and then it will go to a user acceptance system, which will then bring that system up on your used test system, and you can verify it works. And then you can then deploy it to production, but all using Git and text files. So everything pretty we do gets turned back into text so we can move it around. So, and then to the other point, if we go to this model of running it in the cloud, then the cloud is small compared to this kit, and it's reusable and reconfigurable very quickly. Because we just had a new text file committed, and bingo, we have a different system. So, having said that, reconfiguring a Kubernetes system, typically when that's done in IT projects, is you shut it down, you bring it back up again, right? You've got a new. We have to stay on air during that, so we have to be able to bring the new containers in, connect them up, guarantee they're working, and then switch to them while the whole system's running. So we don't get to do the burn it down and rebuild it that most people use in this space. And the same when we do an update, and we will have bugs. It's the way the software works. So we have to do a blue-green deployment. So we bring up another pod alongside the running one. It connects to the same sources. It starts processing, creating the same output, but it can't write to the output because the other one's doing it. And then once it's synchronized, it will say to the other pod, right, I'm ready, you shut down, and it will instantly transfer. So within microseconds, we've cut across. So that means we've done a seamless update of software on the system, which is also quite a scary prospect to have to do. And then because they're broadcasters and conservative, they'll have two systems. They'll have an A chain and a B chain, and we have to update the A chain first and get that up. And then when we're happy with it, we can then cut back from B where we went to while we're doing the updates on that. So, but we've seen what happens when ITV screw up a goal and go to the adverts. They lose millions over it, and they can't afford to do that. So this stuff just has to work. And unlike most IT, not in a few seconds, every 20 milliseconds, it has to work. There is no room for margin on this stuff. So the output, we still have to come out at 20 millisecond intervals. The compute gives us elasticity, so we can manage latency by going a little bit slower, a bit faster, and allowing the scheduler and the CPU to do that work. But when we get to the back end, back down to your phone, your TV, or your tablet where you're watching it, every 20 milliseconds, you will expect to see the next frame arrive bang on time with the audio sync. So eventually, we're back in very real-time world. So,
Ian.
So we talked a lot about the technology, but is it being used now, and for which broadcasters and for which events, and you know, so just tell me a little bit.
We're on a journey.
So that's what
we have been using it for live events. So we have produced them. They're not big events that you'll ever heard of, but we work with people producing large podcasts and things, and we'll come along and do it. We do it for free. We currently are building the technology platform. I was here earlier on practicing my pitching for funding. So we're doing a funding round at the moment to raise money to take this on. We have large companies that supply broadcast kit who are wanting to partner and are actually starting to integrate what we do with them. So our route to market for this is likely to be a white label approach. So we won't be seen necessarily by the end user. It'll be someone in the middle who's already got the customer. And I don't like salesmen, sorry to say it, but salesmen are hard to manage. I like to work with people who understand what we're doing in a really efficient way. So it's better those people have salesmen and support infrastructures and all the stuff that goes with it. Because we like doing the technology. So we should be realistic about what we enjoy and we're good at.
George, you have
another question online from Graham Panton, who's asking, what about 360 degrees? And I presume he's talking about 360-degree cameras.
Like this one.
Yeah, like this one. Yeah. Do you have content like that? I mean,
we don't at the moment. We're talking to somebody who works in the Sphere in Las Vegas, which is a hellish 360.
Yeah.
I think it's something like 200 4K screens that make up the inside, and then another 200 make up the outside to make that surface up. So at that level, the resolution, everything gets very complex, and in slightly different, less than 360, but a lot of film production is now done on pixel volumes. So they'll use LED walls to build a set. Mandalorian is famous for doing this. Most of what you see in The Mandalorian never existed. It's just an LED display wall. It's a very big display wall, and it goes under their feet, it goes over their heads, and they're completely enclosed by it. But those things have 10,000 pixels across. They have to get streaming to it. But those are also doing things like taking Unreal Engine in live. So the rendering is done in games engines. I don't think you call it a game at that point anymore, but the ideas are similar. So that's being fed in. They get even more interesting, just complete sidebar. And once you've got that big volume up, you can shoot 2 or 3 camera angles at the same time and green screen at the same time. Because what you do is you have, most of the time you only show one picture, which the actors see, but then you flash up for 2 milliseconds a different picture, which they can't see because it's only there for a bit. And then you flash up the green, and you have cameras that can capture the frames at the right time. And now you've got 3 or 4 shots being captured at the same time, which makes my head hurt thinking about how you do that. But it means you can capture multiple camera angles. You only have to do one take, which is also kind of interesting. So nothing to do with what we're doing, but this technology is fascinating when it comes down to it. So,
are there any more questions from the audience? Mark?
The the live video feeds, the high capacity video feeds into the cloud providers.
Yeah.
Are the suppliers of the feeds, the broadcasters, are they building dedicated links in? Or is it that it's
might be 5G, it might be fiber. So
into a Google cloud?
Yeah, increasingly we're using public internet now to do this. Right. Once upon a time, you'd have gone, I must have a leased line. That's exactly what I do. But fiber-based public internet now is just uncontended. My feed in Silent Street, I get a gigabit every time I want it. I never have to think about it. There's no contention. It costs me £300 a month. It's an absolute bargain. Some broadcasters will go, no, I can't have that. I need to guarantee full dual path redundancy. Mm-hmm. But you can go to BT and say, I need full dual path redundancy on my circuits. And they'll go, thank you, we love your order. We'll charge you 3 times the price for it. But they can provide that. So when somebody bulldozes the car park and goes through one of your links, the other one stays up. BT have to build systems to make that networking as well. So they have a whole teams up there to do that kind of stuff. And 5G, by using multiple providers, you get your redundancy that way because the different providers have different fiber backhauls from the base stations back to the core.
So have you got a 12 gigabit stream going in, or are you?
No, the one thing that they'll do is they'll do compression, and that compression will depend on the capability of a VIC. So on 5G, you're probably going to do H.265 compression.
Yeah. So you've got a 2 gig
to get it down to 20-30 megabits to get it back up.
Right.
And if you're going to do that, you need to use long op compression to get good quality pictures through, which means the latency goes out on the high-res pictures. But if we do our bit right, we do low latency H.264 for the proxy feed, so that gets back before the high-res gets back. Yeah. So we can do all the processing on the proxy, and then by the time the H.265 has arrived in the cloud and is ready to go, we've already got the action required and go cut here and out we go the door.
Yeah.
If you're doing high-end stuff like Premier League, then they'll be using 2 gigabit JPEG XS, which compresses at about 6:1 and is nominally lossless. If you're doing film work, you'll want to be lossless. Different people have a different view on it. Most directors and producers want the actual processing to be done without any compression, because every time you go through a compression cycle, you lose quality. Some of the competing ideas for this use compression on the networks. They process it, compress it, send it over a lower bit rate. But every time you do that, you use the CPU, so you have to use CPU to make it small enough to fit in the network, and you lose quality. I was going, well, look, that's 2 things you've lost on, and our networking's free, so we don't have to worry about that bit. What's the problem again? So it does depend what you're doing, and using the RDMA to get that high-speed transport from the network card is definitely the way to go.
So thinking ahead, you talked about full HD there.
Yeah.
4K.
4K. 4K. We're looking at the moment. 8K. It's just a number. It's only 4 times the data of 4K. 16K. I mean, in practice, most broadcasters have gone, why did we do 4K? Nobody really cares. At home, you cannot see 4K in your home. Because you can't have a big enough screen and get it in your house to see 4K. What you can see is high dynamic range. So high dynamic range will give you a much better experience than 4K. But in film stuff, you can see the difference. And it's cost. To send a 4K picture is more expensive than sending an HD picture. You need more bandwidth. So.
Do you have any more questions?
I can imagine, David, and the dynamics of the situations you set up with multiple endpoints and all that kind of stuff, that audio can be a challenge with feedback echo. Even if you've got a low latency system yourself, quite often you get quite big delays in Stadia and stuff like that.
So with audio, the particular problem is you want to give the audio back to the talent. So you've got a newsreader, for example. They need to hear their own voice in sync with itself, right? You can cope with 10, 20 milliseconds before you start to go slightly out of your mind, hearing yourself coming back as an echo. So locally, we need to keep that down. So in the cloud, we'll probably do audio in 20 millisecond chunks. If we do that locally, it's 1 chunk to get it in, 1 chunk to process it, 1 chunk to 60 milliseconds, that's going to be too long. So locally, we use 1 millisecond chunks. So now it's only 3 milliseconds of the round trip from the input to the output, sending it back to their ear. And then when we go to the cloud, we just collect it up to 20 millisecond chunks and send it. And of course, you get better compression, better handling of packets, lower packet rates, etc. if you go to larger packet size. But locally, 48 samples at a chunk is how we'll handle that. And we're doing all the EQ, etc. in situ, so we control that remotely. So you hear exactly what you get, and then we send the whole thing back to be mixed in the cloud. But we might have multiple mixers, one locally to do all the local levels, to feed it back to the tenant, and take the raw stuff back to the cloud to do all the processing again. So sometimes you just have to do things twice, because not an easy way around it. But because it's a hybrid cloud system, nobody knows. That's edge computing, so we like to get some extra cloud terms. So that's computing at the edge, is doing all this stuff locally at the venue, and then we send it back to the core cloud to do the final production. So,
George, do we have any questions online?
I think William may have been trying to get his hand up earlier as well. So.
I have one question.
Okay, well, take another question from the audience.
So you think about press conferences, whenever politicians go on TV, there's often many cameras there, and you're operators and all trying to put their own infographics and things on.
Yeah.
Using this system, could you in theory maybe have one camera, and then they all tap into that feed and have their own logos and everything, and so could you do that, or that?
That whole thing is, I was watching some news the other night, and there's about 30 microphones on, like 6 foot long booms, and you can see them all trying to knock each other's microphone out of the way. It's very amusing to watch. It's not just TV, so the microphones will be the press, it'll be radio and TV, so that's a whole mix of things. The TV people, sometimes there'll be an agreement to have a pool camera, but that's normally only when it justifies. Nobody's that interested. Same one guy will share the pictures. When they share pictures, normally they'll send them to each other. So if somebody's got the pictures and they have value, there'll be a value associated, and that will be extracted from you for using somebody else's camera.
Yes.
So if you're paying £5 to get the pictures off someone else, then it probably costs you 500 quid to send a cameraman. You probably send a cameraman, and there's all those cameras there. So it's not necessarily as simple as being technically obvious, simpler to do that. It might be more commercially down to it. And quite often, there'll be an interviewer as well, and he'll want to be in the shot as well. So you can't get everybody in the same camera for interviews. Yeah, it's the way it goes.
George, do we have any other
No
questions
more
online?
questions at the moment. No.
Okay, well,
Cool.
perhaps a final question from me then. So David, what's from an engineering point of view, what's been the toughest challenge and how did you overcome it?
Probably a couple. One is getting people to understand you can do it. And the only way we can get that is we have to demonstrate you can do it. RDMA in front of a TV producer, they're going, why would I care? And to be honest, they shouldn't have to care. We want to keep their world the way it is at the moment. We want to change their world because they have really good people processes for producing content. So we have to work with their process. We can tweak it, but first of all, we have to be the same as the current system. So there's a massive people challenge around this, and it's absolutely stupid to fail to recognise it. And that covers the operators and the designers and the builders and the integrators, etc. All those have to feel they can build their system, and it's not just somebody with Notepad editing a text file to make it work, which some people think should be the way it is. There are not enough Kubernetes people in the world to make that work, so that doesn't happen. RDMA has been phenomenally difficult to make work reliably. NVIDIA, the single biggest manufacturer of data center cards, have asked us to write a white paper on how to use their network cards to do RDMA in Kubernetes because none of their data made it work. So we found out how to make it work. We're still finding out how to make it work because we're still finding little nooks and crannies in it. So that's quite difficult to make work really well because it's got to be secure. So if I run 5 people's system on the same piece of hardware, they're guaranteed isolation, and it has to be low latency, etc. And it has to be 100% reliable as well. So that's been quite a challenge. We've had one guy on this about 3 months now, and he's getting to the end of it. But he came in going, that'll take a couple of days. Like, well, and lots of Kubernetes consultants come in. Oh, they just. And you go, you've never done this before. Well, no, not exactly. No, you haven't done it before. We can tell because it turns out maybe 10 companies have done this kind of stuff. Very few people have actually done it at the level we're trying to do it. And that was surprising, but also not surprising at the same time. So those are the big ones. I mean, the rest of it's just fun. I love writing software. So.
Thank you very much. Okay. And George, any more questions?
No, we're all done.
No, I think we'll call it a day there.
Cool.
So thank you very much again for an excellent talk, and thank you for taking all the questions.
That's a pleasure. Thank you.
So before we finally finish, I'll just do a plug for our forthcoming events. 9th of April, we've got the History of Telecoms by Roger Ward. He's the technical editor of the ITP Journal. We're hoping to do something around AI in music in May, but we haven't nailed down a date yet for that one. I've got to talk to Somdip from the University of York. The next one after that will be the 4th of June, point-to-point microwave from Professor Andy Sutton of BT. There are a few others that are in the pipeline that we're working on, so we will have a full programme for the whole of this year, but these are the next ones. If you're interested in those, please go to our website, our IET EngX website. The URL is shown on the screen here, and all the details about registration for those events are on the website. With that, I'll just draw the event to a close. Thank David once again. For those online, you may disconnect now. For those here in the atrium, we've got tea and coffee available. Thank you.